But one of the really fun things I found in reading up on the aircraft nuclear reactors was the project ended in the early 60s. And then in the 70s, in the oil crisis, it got picked back up, but not by the military who was first pushing it, but by NASA, who was tasked with looking at different ways to try and save the country energy. And they were looking at the fact that we use cargo airplanes and cargo ships, which burn a lot of oil. Can we use nuclear powered aircraft to haul cargo?
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America,
that is willing to
but we're going to need you, the next generation, to finish the job.
Nuclear regulation.
We need scientists to design new fuels.
And focus on net public benefit.
We need engineers to invent new technologies.
Over absurd levels of radiation protection.
Entrepreneurs to sell those technologies.
Then we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero-carbon components.
Unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
All right, welcome back to another episode of the Fire Diffusion podcast. Today we've got an awesome guest, Gerrit Bruhaug. Gerrit, how are you doing, man?
Good. How are you, Mark?
Fantastic. I'm going to go ahead and let you give a quick 30-second overview or elevator pitch intro about yourself.
Yeah, so I am a PhD student out here at the University of Rochester Laboratory for Laser Energetics, where we have the biggest lasers on this side of the country, third biggest in the world. And we do inertial confinement fusion and other exciting experiments with those large lasers. But before coming out here, I did my undergrad in nuclear engineering out at Idaho State University, right next to INL, a very fission-focused place. I became a licensed reactor operator. I have my license still up on the wall from that. And I worked extensively on particle accelerators for isotope production out there. And then, like many young nuclear engineers, I got the fusion bug and thought I would go chase that for a while. And yeah, hopefully I will finish up my time here in Rochester pretty soon, and then who knows from there.
Perfect. So it's pretty atypical that I won't send a list of questions ahead of time to a guest, but I didn't with you because we had chatted before, actually just earlier this week, and just hearing stories and facts and figures that you'd put together was awesome. And I was like, we just gotta have a conversation that we can record. So here we are. It's Friday, 5 in the afternoon for me and 7 for you. And I'm sipping kombucha and you've got some whiskey. And so we're just going to BS about some nuclear stuff. So. It's pretty cool. So I want to focus on kind of some of your experience, your work with your PhD, talk a little bit about fusion, talk a little bit about the future perspective reactors, like the most pragmatic solutions, as well as some of the more, call it, history of designs. I view you as a nuclear expert, and I didn't give you the chance to brush up on anything because I wanted it to be straight from your expert gray matter, which I'm sure you'll do a great job. And if you get something wrong, then we won't give you a quiz or hold you to it. I was thinking about this question before we started, but I don't know, and our audience is pretty broad. Some are very educated about nuclear and some are not. They come from outside of the energy space or maybe the upstream oil and gas space. But thinking about just reactor types in the US, those that are operating and those that have been envisioned. Talk to us a little bit about the contrast in the variety, like historical variety and what's in use now.
Yeah, so the two types of power reactors we have in the United States right now are what are called pressurized water reactors and boiling water reactors. And these are both in the broad category of light water reactors. So they use the same water that you and I can drink. They use lightly enriched fuel, although they can go all the way up to very high enrichment. The Navy uses pressurized water reactors or PWRs to power their ships and subs. And these are a very old, worn type of reactor. And that's why we have so many of them in the United States. And they're the dominant design around the world for power. And I do want to emphasize power. When you get out of power, things get weird and there's all sorts of interesting stuff out there. But in the early days of nuclear, no one really knew what we were going to jump into. There was a lot of different ideas, and the light water reactors ended up dominating for a variety of different reasons. Probably one of them comes down to the fact that we, as a species, understand how to boil water. and we're real comfortable with
It's pretty
water.
straightforward.
Yep, we got
Although
a lot
it's
of
kind of
time.
embarrassing to realize think about how long it took us to realize that you could turn heat into motion.
Yeah.
When all it took was a pot lid boiling, right?
Yeah.
Yeah.
Or there's maybe an apocryphal story of some ancient Greek steam engines, but they just thought they were fun toys. No one thought maybe you could do something with it spinning around.
Yeah.
But yeah, you think about a light water reactor, especially a light water reactor has got very similar operating parameters from the power plant side as to a coal plant. So you think when you're starting to make power plants in the 50s and envisioning them in the 40s, something that matches up with what you understand with boilers and pressure and water makes a lot of sense. But from the very beginning, people knew there was a lot of different ways you could do this because nuclear obviously doesn't need any oxygen. And there's all sorts of interesting neutronic properties. And people were thinking about very exciting designs right from the beginning. And they were building them. There was an entire AEC, so that's Atomic Energy Commission, that's before the DOE and the NRC were generated. There was just one group. And they made all these different reactors at power plant scale, but about 30 megawatts. And they sent them all over the country to try and get a feel for what was going to be best for deployment as power reactors throughout the country. Nick Turin's What is Nuclear website has a wonderful history on all of these things.
Awesome website.
Yeah, just
Fantastic
great.
website.
Definitely visit it. But we had just incredible stuff from the classic PWR built in Shippingport. BWR, the first BWR was actually built in South Dakota of all places. Most people don't know South Dakota had a nuclear power plant. These were all built about 30 megawatts for the power size. It was big enough that it would work and impact the local power grid, but not so big that it was a gigantic investment. There was sodium-cooled graphite moderated reactors. I think it was Nebraska where they deployed one of those, and they tried putting one on a submarine. There's the classic sodium-cooled fast reactor that we all know and love, which operates in a completely different regime and lets you breed nuclear fuel. There's several of those built in various ways.
Isn't that effectively called experimental breeder reactor, EBR?
So there's EBR1 and EBR2, which being educated in Idaho, I have to love. I'm legally required to love those reactors because they were invented there. But there was actually another one built in Michigan, which is a bit infamous, called Fermi 1. And it suffered a partial meltdown. Yeah. It kept running right after the partial meltdown. And the partial meltdown was, as is typical with the story of early nuclear failures, due to just complete incompetence. Someone welded a part in that they weren't supposed to weld, didn't tell anybody, and then it broke off and plugged the coolant loop.
That's right. Yeah. In like the bottom of the drain tank.
It's just complete stupidity. There was no reason that had to happen. But it's infamous because some anti-nuclear people bring it up as we almost lost Detroit, but we didn't. It was nowhere close. Yeah. The reactor was fine. It just sucked to have a partial meltdown, and it made the power company not want to play with it. There was also gas-cooled high-temperature reactors. Peach Bottom down in Florida had one. I want to say there was at least a couple others, and these were just of the power plant variety that people were playing with. There was other much more exciting things being built just at the labs for tests. This is when the molten salt reactor,
the kilowatt scale,
megawatt typically.
But a megawatt test reactor, these prototypes that they were building were significantly smaller than what we think of as nuclear power plants, but they're still producing megawatts, right? This would be a huge diesel generator.
Oh yeah, so it's a fun thing with nuclear. Is those of us, we're all familiar with chemical fuels. So we know if you want more power, the engine's got to get bigger. Those of us in America know there's no replacement for displacement. You just got to increase the cylinder size. But for nuclear, the question is heat extraction, not core size. You can make core, in theory, basically go to any power you want. So I could have something, well, maybe not that big, but about this big, make as many.
Yeah. Holding up a coffee cup for just the audio folks. But yeah, he held up a coffee cup.
Yeah, a coffee cup. I can make something that size, make as many megawatts or gigawatts or whatever you want. The problem is power extraction. You can't pull power. You can't pull the heat out fast enough. But there have been very power dense cores made. I think the absolute most power dense nuclear core made, if I was to guess, was probably the Tory 2 reactor built, I want to say 1961, as part of the aircraft nuclear program. This was to power a nuclear missile. A nuclear-powered nuclear cruise missile that would fly around the world at Mach 3 and just circle the Russians until they told it to go. And it would carry 20 thermonuclear weapons, fly at treetop level, just shattering windows and killing people with the sonic boom, spraying radioactive exhaust out the back and dropping nukes. It was a terrifying, terrifying weapons program. And the really scary part is it all hinged on the reactor. And the reactor worked. They did these tests out in the Nevada desert with the Torrey 2 reactor, and they made a 500 megawatt thermal reactor that was just tiny, and it would power a nuclear cruise missile to any, and the limit was heating of the skin of the missile. The reactor had all the juice you wanted to get out of it. But that's another good example of a very innovative design that was, some companies are looking at what was done back then, like Holosgen has referenced it as something to consider, not the exact setup, but the broad ethos of these just air-cooled turbine-style reactors.
Right.
There was other aircraft reactors that were built. There was one in Idaho meant to power a bomber. They fired up they had a full jet engine array in it. One of my old professors was part of this project, so I've heard quite a bit about it. You can actually go see the engine out in Idaho. They have it sitting there on the side of the road. And it's a relative of the gas-cooled reactors that people are excited about today for high temperature. And this thing was built around a jet engine, and they actually fired up the jet engine on nuclear heat, which no one had ever done before. There had been some basic tests with just trying to make like a ramjet or a rocket, but they actually got the full turbines to spin and everything just off nuclear heat. They even melted the turbines because the reactor could really give it the heat. And the idea was they could fly an airplane with this. But the other fun thing that came out of that program is the famous molten salt reactor. Everyone loved, it's so popular, especially in the more common nuclear discourse. Love it or hate it, it is very common to talk about the molten salt reactor. And that came out of wanting to make very power dense, very simple, very long-lived reactor cores to go on airplanes. It was not meant to revolutionize the power world. It was entirely to power airplanes. There was talk of molten reactors even back into the Manhattan Project, but the actual first one built was to power a nuclear bomber. And there was designs on the board to make a nuclear bomber the size of a 747 that would fly at Mach 3 using molten salt reactors. And it looks very plausible based on the performance of these things. And there's just a rich history of really innovative, unique reactor designs that were, what's really mind-boggling is we're so used to these paper reactors today, right? Someone draws something up and say, this is going to be amazing. And all they have is a computer model or a couple calculations. Back then, computers were really bad and expensive. They just built them. They just went, I wonder if you can make a reactor like this.
And fantastic at just going out and doing it, which is incredible.
Yeah, I heard a lot of stories of the early days in Idaho where they would talk about building a reactor, come up with a rough design in, say, a week, and they would have it running in 6 months. And it's just, some of those reactors are still around to this day. They'll probably live forever. The ATR reactor, Advanced Test Reactor, which has got this infamous, beautiful cloverleaf looking core. A lot of people know, if you Google Cherenkov radiation, it's usually the first picture that comes up. That thing has got some of the most advanced neutronics you could ever throw from a nuclear engineering perspective. They built that in 6 months. And as far as I know, I think they designed it in a couple weeks. It started with barroom napkin sketch and went from there.
That's awesome. So I love that brain dump. And the point of the question was to give listeners or viewers the demonstration, we'll call it, that we only use really 2 types of reactors in the US. And there's a handful that are used for power across the world. But we've built a bunch of different reactors in the history of nuclear, which was something that I didn't know when I started restudying the topic. And I feel like is not well known outside of, call it, nuclear engineering circles.
Yeah, and even within nuclear engineering circles, I find it so interesting. I finished my undergrad almost 5 years ago, and I still learn about this stuff. There's only so much you can jam into an undergrad career, and you're of course focused on learning about what exists and what we're building. But there is an incredible rich history of things that have been built, have been tested, have been thought of, that all have unique potential, especially when we're considering not just making a big electrical power station based on what we know how to make in the 50s. You know, it's 2023. We got to start thinking a little more exciting.
I totally agree. So I want to start with what we know with existing plants. And one thing that comes up is safety and really we'll call it radiophobia that results in my opinion, overregulation of nuclear and nuclear energy. So you live near a power plant in upstate New York.
Yep.
Correct.
RE Ginna, which is the oldest operating nuclear power plant in America.
Yeah.
And also the smallest.
Tell us a little bit about it. Yeah. Give us kind of an overview. I remember chatting about kind of your experience with it.
Yeah, so this was the first nuclear power plant I'd ever visited. So I should back up a little bit. I'm from Montana. We have the only nuclear thing we have is bombs.
Yep.
So I had to leave to go do any of this exciting stuff. And in Idaho, my experience was all with research reactors. They don't have a power reactor in Idaho right now. Hopefully they'll have several pretty soon, but I sadly was there when there was no operating power reactors, even at INL. And moving out to New York, in upstate New York, they built a bunch of they started out with Ginna, and then they built some larger and larger nuclear power plants up here on the lake. And then, of course, Indian Point down near New York City, which is sadly now closed. But Ginna is of the era where they were starting to scale up the reactors bigger and bigger. And it was, I think, probably in the very beginning of that, because it's 585 or something megawatts electric. So a little tiny PWR compared to these 1 gigawatt plus machines that we're used to today. Plenty for Rochester, though, which is not that big of a town. It used to be a larger town industrially, but has shrunk since then. And one of the things I thought was really neat with this is when I finally got to go get a tour of the reactor, it's right near town. It's just right up on the edge of the lake. And I never realized I had driven by it probably hundreds of times and did not know. I knew there was a reactor nearby. I didn't know where it was. There's no big sign. There's no big cooling towers. They did direct lake cooling. They ran all the power lines the big power lines underground so that it wasn't obvious. And upstate New York is very pretty with all these big trees and orchards and everything like that. And the designer of the power plant, this gentleman, Ginna, who it's named for, he was big on trying to integrate his designs into the community. So the reactor also, it doesn't have a big, ugly concrete dome. They built everything up with this nice green color. This is a cup from Ginna. That's the color the reactor is. It's got nice covers over all of it, and it just looks like a big building with a parking lot. And it's the exclusion zone around the reactor is all apple orchards, and you can buy Ginna grown apples, and the people that work there can even hunt on the land where all the deer run around. They used to be able to fish right off the edge of the reactor is what they told us, but that's been banned now. But if you go out into the water a couple hundred yards away where they cut off the exclusion zone, I guess the fishing's still very good because of the heat from the reactor. And it was so cool to go see this integrated thing into the community. I think more reactors need to be like that. And I think the only downside is that Ginna isn't advertised. They should have billboards telling everyone, hey, your city is powered by zero carbon energy, and we make apples for you as well, just because we had something to do. And they should do way more tours. But due to the restrictions on the site safety restrictions in the United States, it's very difficult to get a tour. One thing they were showing us was post 9/11, they did a lot of upgrades to the security there. There's tank traps. We're in upstate New York.
Yeah, what are the Canadians going to invade? This doesn't make any sense, right?
They'd have to come across the water to begin with.
Maine, Connecticut?
Yeah. We also have a gigantic army base in upstate New York. Call the military if there's a tank.
Makes no sense. What a waste of money.
Yeah, there's little sniper towers. The amount of military hardware we saw during the tour was wild to me. But aside from those complaints, one really amazing thing I got to do, and I don't know how common this is, but Ginna was running. It was powering the city at the time. They were coming up on a refuel. They actually did their record, I think the record for the United States fastest refuel ever right after we were there, because they've just had so long. We were talking to the engineers about it, and they said, we've just gotten so good. We actually plan where people park. And we think about like where people stand when we start the refuel so we can do it faster. But they had we were in the turbine.
Lean thinking, man. Six Sigma. They figured it out.
Just incredible thinking. But we're in the turbine hall, and they had us walk up, and they said, go put your hand on the outside of the turbine and feel what 585 megawatts feels like. And I'm a muscle car guy. I love the rumble of the engine, but man, nothing beats that. That was wild. Because it's isolated, it's sitting in the floor, it's not really shaking anything, it's just loud in there. And you go up and touch it and you go, oh my goodness, this is a whole city's worth of power.
So I love your articulation of the beauty and the magic behind this power plant. That, yeah, like you said, when people think of nuclear, even within the industry, that is not what comes to mind. But it's a demonstration of how you can beautify an industrial project. And when you originally described it to me, I was fascinated. I was like, oh my goodness, the little apple orchard, and you can go and hunt. What a great idea. Now, it's more expensive to bury the power lines and make some, call it, development decisions that were probably made that are probably more expensive to develop facilities like that. But if you want to make it fit, in my opinion, it's a demonstration of how you can integrate an industrial facility into anywhere in the world and beautify it. Like, really cool idea.
And just speaking of cost, one kind of painful thing too is, so this plant was built back when things were still happening fast and cheap. It was built in 4 years, and for, I believe, inflation adjusted, it was something like 100, probably not inflation adjusted today, inflation adjusted 2 years ago, something like $190 million.
It's sad that, yeah, that's impactful. The 2 years ago in 2020, dollars were worth a lot more.
Yes, but still, even then, we're not talking $1 billion power plant. We're not even talking $500 million inflation.
So 190 million, you said, for 550 megawatts, right?
Yeah, something like that.
That's incredible. Wow.
Pausing here for half a second, I went back and fact-checked this, and Gerrit was close, but off by about a factor of 2. So he guessed $190 million. Turns out in 2020 dollars, the power plant cost about $432 million to manufacture, which on a dollar per watt basis is still absolutely incredible. I mean, that's like 75 cents per watt, which for reliable power on a beautiful power plant that's carbon free is just unreal. So he said 190 million. I went back, fact checked. It was really 432 million in 2020 dollars. We won't hold moon to it, but still remarkable to think about how cheap that is.
Yeah. And it's it's licensed to run to, I want to say it's at least 2028. The bigger question is actually just the state of New York. They think they can keep running the power plant indefinitely.
For forever. Yeah. That's incredible. So that's what exists now. And the industry needs to talk about it and promote it. And it's incredible, especially the fact that it was built so cheaply. And we should be able to replicate that today. The safety upgrades from 9/11, like you said, make no sense. I totally agree. And I've heard a lot of people within the industry complain about them, and it just seems silly. But let's shift gears a little bit. The NIF event, when I was prepping for this interview, you chatted with Kiefer on Decoupled podcast about 2 years ago. So it was January 6th, 2021, when that episode was released. And you guys were contemplating about when NIF might have been energy positive. So NIF being the National Ignition Facility, and it's happened. And there's been a lot of buzz about it. I'm sure all of your friends have asked you, what does this mean? All of my friends have asked me, what does it mean? And I'm sure we're still of the same mindset that neat science, really tough engineering problem.
Yeah, so to real quick to shill Kiefer's podcast a bit more, I actually did a follow-up with him, I think a month ago on the NIF event.
Yeah. We don't think that one's been released yet, has it? Yeah.
I don't know if it's been released. I can never listen to my own voice, so I have no clue. But yeah, the NIF event was very exciting. We were pumped, obviously. I feel really happy, really blessed to be in this portion of fusion when this happened. It's pretty incredible to build. It's neat to be able to say I was around and I was plugged in when that happened, that we took that step. I'm going to rip off Robert Zubrin's way of describing this, but it's like figuring out how to light a fire. It doesn't mean you can build a beautiful diesel engine tomorrow, but the fact that you can light the fire is a huge step when you could not light the fire before. And it's incredibly exciting to be at this point. I am hopeful that we will see a lot more development on that front. I wouldn't be shocked if we get other ignition or burning plasma events from other types of fusion concepts here in the next 10 or so years. But fusion's a big engineering challenge. It's very difficult to get the power plants to work. There's been a lot of work on the physics of making it happen. There has not been very much work on the power plant side, and it's going to be a big leap to get there. And on top of that, if we just look at the history of fission, there was a lot of learning to get to where we are now. Yeah, reactors weren't all that reliable. They didn't always have this 90+% capacity factor, and we had to figure it out, and we had to have dumb failures. Fusion is going to have to go through that, and it's a more capital intensive project just based on the high tech equipment needed, and we're in a bad time for capital intensive things. So it's going to be challenging. Yeah. The one thing that is nice, at least in ICF, inertial confinement fusion, like what NIF does, and like what we do here in Rochester, is we are connected to the national security world. So we are very liable to get future lasers that can do even better than NIF, that can break the path towards a power plant, and just similar to fission, ride the backs of the military industrial complex to figure it out. But that's going to take a while, and no one's talking about building a new NIF tomorrow. They're talking about maybe 10 years from now, we'll build a new one. It's not something I would bank on, especially if we're talking climate change stuff. I would not bank on turning a fusion reactor on fast enough to make it to really matter.
Yeah, I agree. Tragically, I had investigated NIF and inertial confinement fusion as a young man and even as a kid because I was fascinated. I was like, I can grow up and make this work. And then I went and got oil out of the ground instead. Unlike you, who's actually out trying to do it and trying to make it work and studying it. And that's really cool. I admire you and everyone else in the field for that. I'm curious on your opinion about the MIT group, the Commonwealth Fusion Project. And they've made a lot of bold claims coming out, or they think they'll have great or good success by the late 2020s. I don't know if you've studied that project much, if you have, or if you've interfaced with any of those folks and what's your perspective?
Yeah, yes to both of those. Fusion's a small field. So so they're doing what's called a tokamak, which is the kind of classic magnetic confinement for fusion. What they're doing too is a very obvious good way of going after a better tokamak. The current big tokamak project is the ITER project over in France. It is based on designs that were settled in the late 80s. It's just very old tech. It makes it very big, very expensive. It's running crazily over budget. For the amount of money that they'll spend on ITER, we could have built NIF something like 10 times at least. That also makes me feel good as an American with getting NIF and how it came in pretty good, pretty fast and pretty good, even being late.
How much have they spent? I know the number I have in my mind is $25 billion, but is that close?
For ITER, it is not clear. It'll be at least 25 billion all said and done. The accounting is very opaque because it's an international project. There are DOE estimates of 60 billion.
Gotcha.
By the time they get to burning plasma, specifically when they're injecting deuterium and tritium in and actually getting chain reactions, assuming it all works, there's been a lot of claims of fusion reactors that'll work instantly before. It'll be a lot of money, and it'll be at least 2035 at the absolute earliest.
Okay, but the MIT guys have these
they're going
superconductors that making the magnet better.
Yeah, so in the 80s, around the time they were settling the design for ITER, we discovered what are called high temp superconductors. They're not actually high temperature. They just work at higher temperatures than normal. They work at liquid nitrogen temperatures. But to get really high magnetic fields, you have to run them a lot colder. So what the MIT group is doing is they are still running them at the same 4 Kelvin or 2 Kelvin temperatures, whatever it ends up being, very close to absolute zero. But it lets them get a much, much stronger magnetic field, which lets them make a smaller tokamak, which is definitely helpful. There's a couple downsides with that whole approach, though. The first being is that those superconductors are really expensive and really finicky. Classic superconductors are metals. You can cast them into wires, you can cut them into shapes, you can do all this normal stuff you need to do, and it's not very hard. These are ceramics. You can imagine making a cable out of a ceramic is tricky, and they're made out of very expensive rare earths, and getting everything to bond correctly and get really solid superconducting electrical connections is very challenging. But having said all of that, they have a lot of money. They have a lot of very smart people who have been doing tokamak work for a long time. They basically took the entire group that was running and developing MIT's personal tokamak, which the Department of Energy shut down about 10 years ago, I think, and said, build another one and get private funding, private and public. They are definitely getting public support. And I've seen pictures, they are pouring concrete, they're moving fast, it's exciting. I would not be shocked if they can get plasma to burn and get a fusion chain reaction out of it. But awesome. Similar to the story with NIF, is hard to then go from there to a power plant. And I personally am not a fan of tokamaks. I have no doubt that you can eventually beat one into making net energy, but I think making one make a power plant is much, much more challenging. There's a lot of challenges with the heat extraction and actually getting your power cycle to work. There are actually interesting safety concerns. Those magnets store a lot of energy. They need to be kept very cold. If they are not kept cold and kept superconducting, they can violently fail. We saw that with the Large Hadron Collider a decade and a half ago.
That's a
And
fancy way of saying explode, right?
yes, they can explode. There's ways to
Yeah.
prevent it, but it is a risk, and you're just putting a lot of very expensive stuff in a very nasty radiation environment, and it's not built in a way that's easy to replace components. Fusion makes like 100x more neutrons than fission per unit energy.
So I don't think, that simple fact, I don't think people really appreciate. Meaning, if you're blasting neutrons all over the place, is there any residual radiation on some of the components? So this is something that nobody talks about, especially, and everyone on the fusion side knows it, but they just ignore it when they're like, there's no waste. But you just turned on this power generator, you created a ton of heat, but then you also blasted neutrons all over the place, which then creates residual radioactive material, meaning everything that was in your reactor just became radioactive. And I'm ignorant on how long it might stay radioactive or remain dangerous, or
so it's
so you might educate me a little more on that.
Yeah, it's definitely shorter lived than some of the things we talk about with fission. If you invoke fuel recycling for fission, the comparison stops looking so good. Because the long-lived stuff in fission is primarily fuel, right? It's things like plutonium. The fission.
And actually, I am curious on one specific comparison, which is a fusion tokamak versus a high-temperature gas reactor, like what they were trying to build for aircraft. And I don't know if you've ever thought of those.
In terms of waste, or
in terms of radiated material that might be radioactive after you shut the machine off.
Oh, the aircraft reactor will almost surely have less total. It will definitely have less total volume of material per unit energy. You probably end up about the same in total activity, and the aircraft reactor will remain radioactive for longer unless you reprocess it and process things out.
But is it just the fuel that remains radioactive, or is it also the other components? Because
it's almost entirely fuel.
It's both. But the tokamak, it's not just the fuel; it's the actual machine that becomes radioactive.
It's the low.
And
it's the low
again,
density.
That's the distinction.
Yeah. So you think all of these magnets are radioactive, the tungsten armor on the inside. And so you'll find this kind of fun. One particular issue that is being looked at for fusion reactors, and especially tokamaks or their related magnetic brethren, is the inside becomes unbelievably radioactive in a short term. So you're thinking like on maintenance cycles, it's a problem, right? When you have to get in and replace burnt components because you have a star in a jar, it's not very nice to things. And who
thought this was a good idea? It's hot in here.
Yeah. In fission, of course, we also have really high activity. But the way that we cheat, because we always keep everything underwater or under sodium or whatever, that absorbs all the radiation. You can walk right over an operating research reactor and the water shields you. You can swim in a spent fuel pool and be fine. Fusion, we need to keep the inside vacuum. Maybe we can let air in, but we don't want to flood it with water. And the radiation from a shut down operating deuterium-tritium reactor from activation is so high, you can't send people in at power plant levels, not at test reactor levels, but at power plant levels, you can't send people in. And most robots will die. So there's a whole
the
development.
electronics just melt, right?
Yeah, they just get fried. And there's a whole development program as to how to make robots to do maintenance on shutdown fusion reactors because it's a big issue. And so actually circling all the way back to even NIF, one of the advantages of inertial confinement fusion is we keep all the expensive stuff, and it doesn't have to be lasers. There's a bunch of different ways to do ICF, but lasers are what we like to use right now. We keep all the expensive stuff, the lasers, really far away. You can go walk next to the laser amplifiers and there's no radiation. You shouldn't be there for other safety reasons because there's a lot of energy flying around, but we can turn them off and you're fine. I've done it. I've walked along the laser amplifiers at the lab here in Rochester many times. They're beautiful, incredible pieces of machinery. The reactor vessel is just a big, dumb chunk of metal. And so we can let things get nice and hot in there, and there's not that much in the way of maintenance that needs to happen in the reactor vessel. But even then, the way when NIF got that the ignition shots, the first one that happened last year, the one that didn't get over laser gain, but was physics-wise ignition, the one that happened in August, they didn't have all their radiation shielding in place, all their armor. They have different levels of armor that they can put into place to protect portions of the facility, and they killed the lights in the building with the radiation.
Wait, on the successful NIF shot? Wow.
Yes. And they were
So
so
they-
activated.
By killed, you mean the lights didn't work anymore?
The radiation fried them. They damaged some components because the shot was a surprise, and things were so radioactive. We were wondering so the way that we get the absolute yield measurement, how much fusion did you get, is they have these little copper pucks that are activated, and then you go count them. You count how radioactive they got. You can back calculate to how many neutrons you made. They couldn't send the people in to go get the copper pucks for a week because they
had to
weren't
cool off, and
because they weren't ready for it, and they didn't have all the armor in place. And this thing, it was the first good one was about a megajoule and a half of fusion, of which a megajoule of that is neutrons. Think about a megajoule of neutrons. That is.
Some people don't understand what that is, but it's crazy. Yeah,
it's a crazy number. A megajoule is like a tank cannon round, and it's just that energy in little tiny neutrons flying around. And fusion also has those really high energy. It's wild. And so it makes for a very challenging operating environment, and you have to be ready with your radiation shielding.
So we've scoped kind of the fusion, or we've stated some issues, engineering challenges that exist with fusion. Let's circle back. You're interested in the fission side now. I'm curious on your opinion. There's a lot of advanced nuclear designs, a lot of people trying different stuff. Many people are getting funded. It's a really exciting time in nuclear now, looking forward. In your opinion, what's the most pragmatic solution for kind of developing new reactors? And I'll put some bounds on this. So size doesn't matter, meaning if you're trying to say get the most megawatts out or power out, that doesn't really matter. But which technology selection would you say stands the best chance to potentially get licensed or fall in line or be adapted by society first? And I mean, you can cop out and say NuScale because they just got approved, but I'm curious if you think if there's some other advanced designs that have other characteristics that might be first movers.
Yeah, so obviously the easy answer in the United States, and it's always good to put that parameter in front of it.
Caveat. Yep.
Yeah, the caveat.
Because in China and Russia, they're just building stuff. Like, they don't care.
Even in Canada and Europe, things will be different. The US is a uniquely challenging environment, and it's interesting because we have the best, I would say we have the best.
We're working to change that, Gerrit. We're working to change that. We'll change it. So
fingers crossed.
Yeah.
We have the best labs. We have the most knowledge on this, the best R&D, but it's annoying that taking that step past is hard. But in the United States, the obvious answer is PWRs. The classic light water reactor we already know and love. PWRs, BWRs. I'm really partial to, I have friends at NuScale. They're doing great stuff, and I can't wait to see their power plant get built. I really like the GE BWR or BWX 300. I just really like the design philosophy that went into that. And I like how BWRs are very fast to ramp. I'm angry that they're building it first in Canada with so much GE stuff being here in New York. It'd be nice
Sweden.
to build in New York.
Just wait. So I participated in a conference just this morning that was put on in Sweden, in Stockholm, and you can dial in virtually. But the lady in charge of nuclear in Sweden said, "We're open for business. If you have a design and you want to sell it to Sweden, come talk to us." And there's the GE Hitachi guys there today. He's like on camera. He's like, "We'll come talk to you. Sounds great." So just watch. I bet it happens.
Yeah, I think they have a compelling design. GE's got a long history of good nuclear production. People like BWRs. They're a bit spooky when you first learn some nuclear engineering. As a young nuclear engineer, you're like, control rods from the bottom and boiling coolant. Ooh, that sounds freaky. But they have a long, good history. They're well understood. And there's this persistent myth that nuclear can't load follow, which is so dumb. If it couldn't load follow, we couldn't drive a submarine with it. But beyond that,
We'll just keep saying that. People will catch on eventually.
I hope so. But BWRs specifically are extremely fast in load following. It's a problem. The grid operators can actually force the reactor to load follow without the reactor operators being in charge, and they get very angry about that.
I mean, that's Last Energy's design, right? With the Open 100 project. And
I think they're PWRs. I'm not sure though. I'd have to
I
check
thought it was
again.
a Gen 2 BWR. I'll challenge you to go check that out. So
Yeah, I'll have to check it out. Either way, both of them can load follow just fine. It's just BWRs are infamous for being so fast and love doing it. There's other
yeah.
nuclear economics and fuel damage reasons why we don't like to load follow with those reactors, but they 100% can do it, and fuel is better now than it was in the 80s when people were complaining about load following. We have much tougher fuel. Anyways, those two are the obvious, easy answers. The other one, I am very excited about the Natrium reactor from TerraPower. It's EBR2 made big. I love EBR2. I love a sodium fast reactor. I like their inclusion of thermal storage. I think that's clever. I like that they're building it in Wyoming and on an old coal-fired power plant. Growing up in Montana, I've seen the impact of coal jobs. I would love to see a bunch of those built in Montana. I can think of many nice sites where they would go. And I've actually heard a lot of conversation when I go home. People ask me about that. They said, why are we not building one here? How do we get that built here? We need those jobs. That looks like a great way to power the state. And the nice part is sodium, although the NRC is a challenging regulator to work through, large sodium cooled fast reactors, people have worked on licensing those before. And one of the, to give the NRC some credit, one of the issues they have is they're pretty short staffed and they don't have people that know everything about every type of reactor that all these companies are trying to get licensed. But finding experts on sodium cooled fast reactors isn't that hard in the United States. There's a heck of a lot of them. So it's more likely that one moves forward. It's got a nice heritage to sit on. And man, you want to talk about load following. A sodium cooled fast reactor,
Can do anything. Yeah.
Absolute lightning on the power grid. People will love it. And then the X Energy with their high temp gas reactor, both of those companies have big DOE support. That helps a lot. And both are working on these designs that have a lot of heritage. And that helps you get through a nervous regulator.
Yeah.
And they have big customers, right? X Energy's got Dow coming for them. TerraPower's
It's genius, right? I imagine their sales cycle has been 2 to 4 years, if not longer, to get some of those contracts in place. But once they've gotten them in place, like it's anchor tenants, it's great business, great big business. Very impressed with them. I feel like we've run the gamut, meaning we started very elementary at the beginning of this discussion and have just launched into kind of many of the advanced systems and jumped into the lingo, which is, I feel like, necessary, meaning anytime that you're recording stuff to make public, you want to try and create something new and add to the conversation, which is good. And obviously, we're already coming up on an hour and just going to have to do this again or more often.
Oh, yeah.
So if anyone's listening and they are curious about those designs, go start Googling because there's tons of information about all the designs that we've mentioned so far. I'll say I'm most bullish on the opportunity for small high temperature gas reactors. And I don't know, I talk about that a lot, so we don't have to go into it now. But I do want to segue with that into some of the applications that we talked about right off the bat with nuclear, meaning there's space, there's power in space, there's the stuff that they tried to do in the 50s and 60s is just incredible. The fact that they tried to power an airplane, we just talked about emitting neutrons and radiation in a confined space, and we've now got these containment domes and trying to control radionuclides. But these guys were putting it on an airplane, and they literally flew one, right?
Literally flew one, and they were that terrifying missile I was talking about was actually just one congressional approval from going. They had everything ready to go for a test flight. They were going to launch from San Diego and circle it around in the ocean and then just dump it. And it was actually the U.S. military that said this
hilarious,
genius. Yeah. The U.S. military, the Department of Defense said, no, this is too provocative. We're canceling the project, which is wild. But just talking about the radiation shielding, one other interesting thing I found diving into this aircraft reactor stuff, I've told you this and I'll say it on camera now. A big part of this is I realized about midway through my graduate career that I feel like I wasted some of my time in Idaho. Not that I didn't have a good time or learn a lot, but I was around all these incredible older nuclear engineers who had done incredible things, and I didn't ask them questions about some of these projects. So now I've been trying to read up myself.
Shame, Gerrit, shame. You got to always ask the older people, ask the mentors. Yeah, don't be afraid.
I think part of it is I just didn't know enough to know what to ask. And now I have a million little questions, and I've been getting back in contact with them and learning about some of this stuff from people that were there that built it. But one of the really fun things I found in reading up on the aircraft nuclear reactors was the project ended in the early 60s. And then in the 70s, in the oil crisis, it got picked back up, but not by the military who was first pushing it, but by NASA, who was tasked with looking at different ways to try and save the country energy. And they were looking at the fact that we use cargo airplanes and cargo ships, which burn a lot of oil. Can we use nuclear powered aircraft to haul cargo? And because it's going to be a civilian thing, they had to think about how to make it ultra safe. You can't take the risks that you could with a military aircraft. And they looked at shielding that would act as armor for the reactor as well. And the shielding would be so thick and powerful, or good at stopping the radiation, that you could sleep on it and there wouldn't be any issue with the reactor at full power. And then they said, let's see how armored it is. Can it survive a crash? And they made these little test dummy stand-ins, I think they were like 1/10 size, and shot them on rocket sleds and proved that they could survive an aircraft coming in and crashing and the reactor wouldn't leak. And they even had one come off the rocket sled. I have these old black and white pictures of these things flying into walls and stuff. And they had one come off the rocket sled and go bouncing down the road and crush a car. And they said, well, the car's destroyed, but the reactor's fine.
You got to email a picture of one of those to Emmett Penny and have him include it in Crom's blessing in grid brief.
Oh, yeah, I do. I should send that to Emmett.
Yeah, he'll love that. I want to finish on the gas core reactor. So you have a Twitter thread about this, which is awesome, and you described it to me briefly. I'll give some background or context. Most people, when they think about nuclear fuel, unless you've actually studied the industry and understand what nuclear fuel is, don't actually have any idea what it is. You know, I pictured the blue glowing something, or the green goo from The Simpsons, which is totally inaccurate. All nuclear fuel is generally solids, meaning like it's metals, uranium, right? There's atoms and elements of uranium that we've just separated isotopes, and then we combine it in such a way that an effect that when you change the geometry or modify the geometry of how you arrange these metals, then it creates a neutronics effect. Am I thinking about that correctly? That you've got more neutrons going out and colliding with other atoms, and then they fission, which is incredible. But essentially, they're solids, right? So you've studied, or you identified a system that didn't use solid uranium and had some interesting characteristics. So let's give us kind of an overview of that.
Yeah, and I guess real quick, actually in the United States, most of our reactor fuel is oxides, so a ceramic. But there's a big push back to metal. Metal is it's a whole debate, and I got those wrong. Yeah. No, I just wanted to point it out because it's fun to think that it's the fuel's like your plate.
I guess I meant they're not liquids or gases.
No, they are not liquids or gases. And there's of course the famous molten salt reactor, which does have liquid fuel, but we're going a step beyond. So this was thought up. A gas core reactor is not a gas cooled reactor, even though it's easy to mishear it. The idea is the classic thing you hear the molten salt guys say is the reactor can't melt down if it's already melted. And the gas core, if there was any gas core guys are still around, would say the reactor can't boil if it's already boiled. And so the idea is they'll let
meaning the fuel, the uranium, is literally in gaseous form.
It is in gaseous form. It can be pure gaseous uranium itself, or more commonly, uranium hexafluoride, which it will turn into a gas actually at a pretty low temperature, which is good for experiments. I think it's 50 degrees above background or above room temp or something like that. Anyways, this whole thing, people were thinking about this even in the Manhattan Project, because they're moving a bunch of gaseous uranium around for enrichment, and they're going, you could totally make a critical reactor with this if you got your arrangements right, because they had to think about how to not make it critical. And the Soviets first played around with this, and they just had gaseous filled fuel rods, just trying to understand what you could even do. And then the United States, in classic fashion, went much further at Los Alamos, and then finally in Idaho. One of my old professors built this thing where they just had a sphere of gaseous uranium in a cavity, and then they had reflectors on the outside. And the big advantage here is that you can run that uranium gas or hexafluoride gas to just incredible temperatures. You'll hear some people refer to it as a plasma core rather than a gas core, because it would, depending on how you want to define it, it will become a plasma.
Yeah.
And
how hot? Give us
how hot do you want it? They talked about 5,000 degrees Kelvin without even a blink. No one has done that. All the tests were much lower temperature, but it wouldn't be challenging to do. And the advantage there was, the whole idea was to power rockets. Now, there's a lot of other challenges they found with making nuclear rockets use run with gas cores, but the idea never really went away because one big advantage, there's two big advantages here, aside from the temperatures. The reactor is unbelievably responsive because of the fuel being liquid like that, or gaseous. It just responds instantly to changes in power. And the poisons naturally go out. So the burnup of the reactor, you can burn the fuel to 100% depletion. You just keep putting fuel in as you burn fuel, and the poisons, the fission fragments just leave. You're naturally reprocessing. And there was designs for all sorts of very interesting gas core reactors for power. They talked about literally gas core reciprocating engines to power trains. They looked into these really incredible kind of gas turbine-like gas core reactors that would have crazy burn up, very high power output, would be breeders. It's a really compelling concept, and it's not something I would go put in my nickel down today. But man, there's something to be said for what you could get out of it. If we put the R&D in, there was very few ever made. The project ended in a whimper with the end of Apollo, but it seems like something that could be picked back up and some really exciting stuff done with it. Even looked into, you can actually use the gaseous core to directly act as a laser. So you can get large amounts of industrial grade ultraviolet light coherent. So you think like maybe a semiconductor fab, self-powered, for instance. That would be an interesting concept.
That's awesome. So I know we threw shade at Fusion for having some engineering challenges, but I did want to end with this discussion on kind of an advanced application and really core design, right, of this incredible physical phenomena that is fission, to give people hope and spark some optimism and also like some curiosity. Because when you talk about this, it sounds like a technology that is science fiction. When it was tested, it is real, and yet there's still so much unknown about it that the applications that could be realized and use of it and like the benefit is huge. I just think it's fun to think about. And that's just one case. You listed off to start this discussion 10 to 20 different reactor types and models that have been built. And I think when I've counted them, it's like 50, 60 prototypes that we had actually built, and there's dozens more designs. So anyway, there's just so much opportunity in nuclear and with fission and to move forward and advance the science and the technology. So.
I 100% agree. I think we're in the very early stages of the nuclear era, and there's so much more that we could do. It's talking about it like the designs are over, or like people in 1820 talking about they've solved how to burn coal.
Yeah, exactly. Cool. Gerrit, thanks so much. We appreciate it.
Yeah, thanks for having me on.